And we have nice presentations today of microcore from Klaus Schleissiek from Germany. And Frank Russo will present us the ESP32 Force Bluetooth communication. Rob Probin also with Micromouse challenge and Micromouse in Force. We have Matteo Vitturi from Italy showing us a wonderful sound experiment on his Spectrum Force. Bill Ragsdale with another lesson and class about structures. And Brad Nelson, he will talk about the news with ESP32 Force and the latest developments. So, gentlemen, here with you, the space of ESP32 Force with Frank Russo. Let me unshare my screen. Frank, are you ready?
I am. Can you see my screen now?
Perfect.
Is the volume coming through okay?
I think so.
All right, very good. Good morning, everyone. And Peter, thank you very much. Before I begin, I do want to thank Brad Nelson. His name came up here a minute ago. I want to thank him for his help in working on this Bluetooth project I have, as well as recently and assisting me with some of the words of the new structures vocabulary. I began looking at my desk and I had a bunch of ESP32 modules on my desk, all the dev mods. And most of them were in use except two, and I decided, why can't I get the two of them to talk to each other? And after digging for a while, I found out, well, Bluetooth seemed to be the way to do it. And I started playing with Bluetooth one-on-one between my computer and my phone with one unit going back and forth. But I wanted two units to talk to each other. But I also wanted to be able to observe the communication going on. And the way I did this was by running two versions of Arduino at the same time, 1.819 and 204. They will both run simultaneously. It was interesting. And I had no problem with that. Oh, bear with me a second. Here we go. I want to bring up a couple notes trying to get these two units to talk to each other. Again, I said what I did is I had both Arduino 1.819 and 204 running simultaneously. This allowed me to observe the communication between both units. An important point here, when connecting two units together, only the controller can actually initiate a connection to a receiving unit. They have other names for them. The Bluetooth software may call it master and slave. I've changed it to controller unit and a receiving unit. But only the controlling unit can initiate a connection. A receiving unit cannot. And the receiving unit must be turned on first. It has to be visible and sitting there waiting for a controller to make a connection to it. Come on. One of the things I ran into with the Bluetooth software is errors would occur, but I could not see them. And after digging for a while, I realized, looking at the software and then after Arduino, that the core debug level, of course, was set to none, which is normal. But if you set it to verbose, the Bluetooth software itself will send you a lot of information, debugging information, error codes, and other miscellaneous statements as it's operating. But if you don't turn it on, you won't see any of it. This is how I learned that a receiving unit cannot initiate a connection with a controller. Once I turned it on, I realized I was getting messages that said, hey, the receiving unit can't do this, only the controller can. Another issue I had was with the dev mods, the Bluetooth is not enabled by default. You have to force the enabling of Bluetooth, and you have to go into the fourth INO file sketch in order to do this. The dev mod doesn't have PSRAM, and that's one of the criteria in the compilation of the fourth code. Is it looks for this, and it also looks for a camera. And if it doesn't find either of them, or the PSRAM is disabled, it will not enable Bluetooth. So you have to force it on your own. And the way to do that is kind of simple. This line I have here, defining the Bluetooth support, you have to add that yourself. And if you go into your Bluetooth code somewheres around, well, in version 7.10, it's around line 67 to 80 in there. There's a section called default options. You simply add this to the bottom of the options. This will automatically enable Bluetooth for you. Another issue I had, which thanks to Brad, he helped me figure this out. When Bluetooth, once Bluetooth was enabled and I began running Forth, I noticed my system heap, well, Brad noticed it actually, system heap had 95,000 free. Nowhere's near enough. It needs to be excess of 120,000 bytes free. So, I'll show you in a second, Bluetooth is a hog when it comes to your memory usage. So in order to get this 120,000, you need to add into either an auto exec file or type it in manually, the following two lines. Adding the internal and the ESP vocabularies, you type in the following line. I set mine at 150,000 free heap, and this will relinquish. There is, Brad said something about there is memory floating around, and when you do this, it will free it all up and put it on the heap for you. I don't understand it. It works. Once I do this, all of a sudden I pop up with 155,000 memory, free memory available, and Bluetooth will run. The Bluetooth would not run with 95,000. I attempted it, and pretty much each time it would just crash out or just go nowhere. It would come on and you lose control of the operation at that time. So I ended up putting this into an auto exec file. And so when I come on, it's automatic for me. As I said, Bluetooth is a hog. When you enable Bluetooth, normally when I turn on Forth, I am only using about 81% of my program storage. I'm sorry, 41% of my storage space. But when Bluetooth is enabled, it comes up at 81%. So a lot of storage space, program storage space is being used by Bluetooth. This is just kind of general information for you. The Bluetooth library can be found in the glossary. This is fantastic. Of all those words there, I think there are 11 or 13, I think there are 11 of them. I forget now. Anyway, you're going to use about 9 of them in actually initiating Bluetooth and making it operate. There are others there. Some of them I haven't used yet. I'll get into them myself later. But in order just to get 2 units talking to each other, about 9 of those words in the glossary will be used. And this is a very good source. I kept it beside me the whole time. Now I'll talk about setting up a receiver. In order to set up the receiver, what I did, of course, was I needed to declare a buffer space for information to come in and out of. The first command executed is very simply serial BT. This opens up a handle to the Bluetooth itself. It returns an address. You've got to save this address because every command afterward is going to be using the address. Second thing you're going to need to do is enable the SSP. SSP is a simple serial pairing. You don't have to use this. I found it seemed to make the communications between the two flow a lot easier. This is nothing more than a flag. It doesn't really do anything except turns a flag on so the Bluetooth software knows you want to use simple serial pairing. Other than that, it's transparent to you. You don't need to worry about it. Next, you need to, begin You have to begin the Bluetooth by giving the unit you're working on a simple name. This particular case, it was called the ESP32 BT slave. Call it anything you want. It doesn't really matter what you call it here. The 0, second object, is a flag that simply says, I am a receiving unit. If it's a 1, it would say I'm a controller. If it's a 0, it's a receiving unit. The BTO, that's the object you received up here when you first started, and then you tell it to begin. This will simply return a flag, true or I won't say true or false, 0 or 1. And at this point, if you were to pick up your phone or go to your computer and check your Bluetooth, you should see this name pop up as an available device for connection to. Now, after this is nothing more than setting up a loop for checking to see if you have any available data coming in. Very simple command. Again, the handle, and then this Bluetooth, the serial Bluetooth available command, and it will return an end, the number of bytes, if there's anything available. If there's none available, of course, that's a 0. So you set up a loop, check to see if there's anything available, and you just keep going through it. Once something becomes available, you need to read those bytes into a buffer for yourself and then process them however you want to process them. So again, simple format, you have an input buffer, the size of the buffer, the handle, and then the read command. When it reads, it'll bring in a value, the number of bytes it actually read in, and you save it to a counter for yourself here. Only other point I want to make here, I'm going to back up for a second here. After you have received the information in, you're going to respond back to it. And all responses coming either in or going out should have a carriage return line feed on the end of each string. 1310, decimal, OD, OA, hex, but every string needs to have this at the end of it. I also found this out when connecting a simple ESP32 to a device other than it's another ESP32. The communications back and forth, I wasn't getting any, or I was getting it, but when I send it out, I wasn't getting anything receiving on the other end. And what I found out is I wasn't transmitting the 1310 at the end of all my strings. Once I did, the outside device was suddenly receiving what I sent to it. Sending data out, very simple. Your output buffer, a size, your handle, and you write the data. It'll also return a number, and that number is the number of bytes it actually sent out. The 1310 kind of acts on the end of the string as a signal to Bluetooth that, hey, this is done, go ahead and send it out. If you don't do it, Bluetooth software seems to want to build its buffer up until it's full and then send it all out. So by putting a 1310 on the end of your strings that you're transmitting out, this will kind of force the buffer to send it out. Another command I found useful, of course, was a flush. I usually either drop or evaluate the number of bytes coming in. I wait just a short period, grab my handle again, and I do a flush. This forces Bluetooth to make sure that its buffer is empty. I found it handy. I found it very useful in that at times I would notice communications were delayed, but if I put this in there, they're not. When I do a write and a flush, the data is immediately received by the other unit. And of course, once this is over, your application is done, be sure to end the serial communications of, again, your handle and the BT end. Otherwise, the Bluetooth will keep running on your unit unless you turn it off. The controller is almost the same, not too much different, except at some point in here, we need to make a connection. We start off with a new that returns a handle for us. We enable the SSP. We assign a name. That's one that happened, just called the master. And again, here's where it changes. I put a 1 in here instead of a 0. This signifies to Bluetooth that it is a controlling unit. It will also return a flag. And again, at this point, If you open up an external device somewhere, your computer, your phone, you should see the name of your unit in its Bluetooth device list. This is where it changes. You need to make the connection. You force the connection from the controller to the receiving unit. One or two ways, either by name or by address. I have not explored the use of the address. It is supposed to be slightly faster, maybe a second or two faster, using the exact address, the MAC address. That versus using the name, because it has to look the name up and convert it to an address. But I found that it's not a significant amount of time, and so I just happen to use the name. Put the name of the unit just as you have it broadcasted. The handle for the controller's handle, all right, not the receiver's, the controller's handle, and you make a connection. If it is successful, it returns a flag. Of course, if it is successful, it returns a 1. If it's unsuccessful, it'll return a 0. I believe that's correct. And then I usually wait about 50 milliseconds and execute this connected command. I can't explain this command in full detail here. I know it helps. Which if Brad's here, hopefully he'll jump in on this one. I believe what you're doing is verifying that you have a connection between the receiver, the controller, and the receiver. It doesn't, it returns a flag, but for the most part, I just dropped it out. I just executed the command and continued on the way. Again, all outgoing messages have to have a 1310 ODOA on the end of all strings. The communications is the same. You have an out buffer, you have a size, handle for the controller at this point who's sending it out, and a write. A return is made on the number of bytes sent out, and I do a flush again. This is a simple communication was nothing more than a loop on both ends, a loop to receive data and send data. What I did on my first simple test was that once the connection was made, the controlling unit just sent out a simple command calling receiver, and the receiver, once receiving it, sent a command back, acknowledged. And I did this back and forth a couple times to verify the communications, but also measure the time interval between sending out and receiving a communications. Again, once everything's done, you make sure you end your Bluetooth connection, otherwise it keeps running. Handshaking I found to be very tedious. The CPU is running, well, it's not a fast CPU. What are we, 240 kilohertz, whatever the ESP is. It's not a modern day processor running at very high speeds, but it is fast. It's much faster than the Bluetooth is. And this, your application will be sending out information faster than you're getting it back in again. And I noticed this coming back and forth between sending and acknowledging it. Had some delays in there. And I determined, for example, my 2 units to send the command out and the receive acknowledgement back was taking as much as 2 full seconds, 2,060 milliseconds. That's a whole lot of time in computer time and computer cycles. But you've got to keep this in mind. When you're setting up communications between these 2 units, there is a long delay between sending out and getting back a signal from the receiver. Yours might vary a little bit different. I'm delving into mine to see how I can speed it up a little bit, but there just seems to be some built-in delays that you have to account for when you're working with two of the units back and forth. The ESP32 is just a whole lot faster than the Bluetooth software is running. This was just a small example of my 2 units. On the right is the master, which is the connection, and on the left was the receiving unit. Again, it comes in with a handle It's actually nothing more than an address to the BTU, to the Bluetooth unit. And then little notice to myself that the master was visible, the other unit was visible, the receiving unit was visible, the connection was successful, and I had outgoing data. The outgoing data was nothing more than master unit calling. That was the words it sent to the receiving unit. And here, as I show you, I have incoming data and acknowledgement sent. And I did this 5 times down the road, down the line here. Later on, I had gone and put in an elapsed timer measuring that time interval on each one of these. And it was, the very first one was the slowest. It would come in at 2100 milliseconds. After that, each signal after that was almost dead on at 2060 milliseconds, pretty consistent there. And that is about it. It is very simple setting 2 of these units up. I have since gone, taking this basic setup I have and incorporated it into an application where the receiver simulates control over 6 sensors, where it can report the status on or off, and then a reading from the sensor. And then the controlling sensor, once every minute, would go and say, would send it a signal, send me a check the status of all 6 units, and then if it was on, it would return a signal for it. And I had this running for long periods of time, back and forth, just to watch the communications. It was a simulation. It would randomly report a sensors being on or off, and if it was on, it happened to return a value, and I was able to do this. And what I did learn in this is that going through 6 sensors, asking for a status and then asking for a value, a lot of time passes. I was doing this once a minute, rotating through all 6, and I was taking up almost half a minute just doing it. A lot of time goes by. And one of the changes I made just really very much recently, and thanks to the structures vocabulary we now have, is I have the receiving unit bundle together all 6 sensors in one stream. So I send a command for summary, and instead of doing one at a time, it bundles all the status of all 6 and a reading for all 6 if available into one short stream and sends it right out. So again, within a 2-second period, a signal goes out and a response comes back in, giving me the values of all 6 sensors. All right, Peter, that's it. If anybody's got any questions for me.
Excellent talk, Frank.
Thank you.
Very interesting. Someone has questions to Frank. I see on the chat there is a question from David.
Yep, that's me. Yeah, I was just wondering about the CRLF line endings. I was thinking probably that's because of the SSP mode. The Bluetooth, the serial communication protocol in Bluetooth doesn't care, right? There's nothing in the spec that says look for a line ending and then send. You pass it a block and it sends it. So I think that's probably something to do with the implementation, using that to identify the end of the block so it can send it, rather than specific to Bluetooth.
Thank you. Maybe.
What's your goal with this implementation, Frank? Do you plan to use it for something special with sensors, and what is your objective?
As I was explaining just at the end, yes, I only began emulating some sensors on the receiving unit, but it is to go in and actually do the communications between the 2 of them, where the receiving unit is going to control 6 sensors. I have multiple thermocouples, 4 thermocouples, a room temperature one and 3 monitoring temperature in another area. And temperature, there's a humidity sensor, and I can't remember what the 6th one's going to be, but my receiving unit will actually be controlling these sensors, and the master unit will then be going back and forth, checking on the status of all of these sensors, making decisions, and sending a response back to the receiving unit. And also the master unit or the controller will be updating a web page as well, in order all the information will be available on a web page.
I see Atle has raising his hand and Don. So we begin with Atle.
Well, I have two questions. You said you had to send a CRLF sequence at the end of a string, right?
Yes.
In order, yeah. Okay. So do you have to chop them off when you're in the receiving end in order to get the string back?
When I get a string in, that string is parsed using a structure, a data structure. So I'm ignoring the character return line feed on the end of it. The string that's coming in is a data structure type. It's sent that way, and both the receiver and the controller have the same structure. So the controller just refers to each of the points it's looking for in the string. And so I'm in my application, I'm ignoring the ODOA. It's to me, it's not even there. If I actually look at the string itself, yes, it's there, but I'm not using it.
It's there, so you have to chop enough to get the string back that you had.
Yes.
Yeah. Okay. That's one question. The other question is, I was planning to use this Bluetooth thing to interface with a Sony PlayStation controller. Now, one of the problems there is that you need to download some kind of Windows application in order to discover the MAC address of the controller. But have you found a way to do that from the ESP32?
Yes, there is. If you'll go to the glossary, there is a command at the very top of the glossary that you can execute, and it will give you the MAC address for your unit.
Oh, your unit, but scan for other units on the Bluetooth network.
Oh, no. I don't, I'm not familiar. I can only get the MAC address for my unit.
Okay. All right. Excellent. Thank you.
Yes.
Don, you have a question? Please go ahead.
Yeah, that 2 seconds puzzles me, because from a hardware perspective, it should be a lot faster. Yeah. If you're gonna do like what Alfie wants to do and use a hand controller, 2 seconds ain't gonna cut it.
I've been thinking about that quite a bit. Yes.
Yeah, I'd be fascinated to hear what Brad has to say about that, since he's an expert in that area. I think it's really great, the stuff that you've done, and we'll be looking into that. Thanks.
I had put delays in my communications, and at first I had no delays. And what I was finding is information was coming in too fast, or I was requesting information too quickly, and things weren't merging. They weren't blending. They were, 3 things would come and go, and instead of blending, I was getting, this kind of thing, and it became a headache. So I put delays in there of about 300 milliseconds in certain points, and sometimes as much as half a second in some areas, in order to keep the delay from overlapping the communications between the 2 units. I'm going to go back and play with that some more on a very simple basis, and see how I can change how I am doing things on both ends to cut that time down, but yet not lose any data.
Okay, guys. Excellent presentation again, Frank. Thank you so much for this wonderful talk, and we wait for next experiments you present on the group. Now it's the turn of Rob Probin with the Micromouse.
Hi,
Are you
everyone.
ready?
Yeah.
Go ahead,
Right.
Rob.
Let's see if can everybody see my screen?
Excellent.
Right, let me go full screen and see if it still works. Can everybody still see it?
Perfect.
So these, I think you guys maybe have seen this robot on the 4th 2020 group. I label, I mean, most of the stuff's obvious, right? So apart from this particular one is a open source design that I was involved in. It's got infrared sensors on the front, although some people use visible light. This design was originally designed around an Arduino Nano, although on this particular one, it's actually quite trivial to modify it for the, there's an Arduino RP2040 Connect, which is a Raspberry Pi Pico design, which is what's fitted on here. There's also a Maker Pi RP2040 Nano, which is significantly cheaper than somebody else has used. Towards the back of the unit, you see the wheels, and inside those wheels, inside the plastic holders are micro metal gearboxed motors with a micro metal gearbox on board, and on the inside, or right on the inside with those colored cables, that's where the motor feed is, but also the magnetic encoders on the shafts, so the back shafts of the motors. So these magnetic encoders actually are off the shelf from Pololu. They've got about I think 12 pulses per revolution of the motor. The motors on this specific one are 20-1 motors. I think the wheels are maybe 30 millimeters, and you can probably work out the number of pulses per millimeter on that. This is not my only robot, but I thought it might be interesting to just give you a basic info. The design is actually on GitHub and on the ukmars.org website. I know some of you have been on one of my Micromouse talks before, but let me just show you what this involves. So, I mean, the competition as it is now is actually discussed by IEEE in, I think it was 1977 and 78, but the competition as we see it today is from 1980. So it's been running a long time. They run competitions in the US, in the UK, in Portugal, in various other European countries, in Japan, in Korea. So it's quite a popular competition still. This mouse you see in the maze isn't mine, but I thought it was interesting because it's got visible LEDs and visible photo transistors. So not everybody uses infrared. If you've got maybe a Raspberry Pi camera with without the IR filter, you can put it on the mouse. So you can see where the spot is appearing on the walls, because obviously targeting the emitters is interesting on an IR mouse. And then the photo transistor alignment's a bit more tricky. You can also see at the back, at the top right, you see those blue shapes on the wall. This is actually the competition maze from, I don't know if it's from this year. The competition was on the 1st of July, and that's we use automated timing gear. So there is a sensor in the middle of the starting cell, which is the top right, that tells you where the mouse is there, and there's one on the exit gate as well. So that's the classic Micromouse. This is sort of the size of it. It's just over 3 meters. Each cell's 18 centimeters, which sounds huge, but when you're trying to do a robot, it's, you know, there's a fair amount of timing constraints. In the 80s, they used over-the-wall sensors. So they use sensors that pointed down. Generally, however, because of the moment of inertia, they're all on the body. People have tried various other sensors, things like ultrasonic and cameras. There are some Japanese camera mice. I've got a camera mouse myself. It's tricky, right? And IR sensors are very fast, or even visible light sensors are very fast. Some of these mice, I mean, the mice that you said at the beginning can do about 1 to 2 meters a second, but The competition, the fastest in the world mice are a lot faster, and they turn at about 6G, the fastest mice in the world. There's also a half-size competition. So from a maze building point of view, the walls are much smaller. These do things like 3D print. It's much more suitable if you're trying to do it on the kitchen table or something. The problem is that the mouse is obviously, you know, it halves in every direction. So you're trying to build the same electronics into an eighth of the volume. So that's been challenged. We did run some mice this year in the UK. It's quite a popular competition in Japan, but the extra requirements to fit it all in provide, you know, especially if you're doing it as a hobbyist, it's extra challenging. We run some other competitions as well, just for your information. Most of this talk, and I'm aware I'm on time pressure from Peter, but we'll see how far we get on, and maybe I can run the rest of it. But the sort of control theory stuff applies for line follower competitions. So there's full size and half size line follower competitions, and also the bottom right is the drag race, which the mice just have to get to the end and then stop. It's very, very popular with school kids, right? That is because they get to manually start. We've got a manually start rule rather than auto start, and doing things really, really fast over several meters really appeals to kids. But we had a lot the line follower competition, even the maze. We've got a lot of school kids running this as well as university students and sort of more senior hobbyists doing it as well. So there's a good breadth, and the only challenge is you're obviously doing software, hardware, mechanicals, control theory. There's a whole bunch of interesting stuff that happens, and I guess there's a few of your robotists on the call, and it's sort of an interesting hobby. So I was going to talk a bit about some of the control theory stuff. At the bottom, I've got a list. I'll try to post these. This presentation is quite big, but I'll PDF it up and reduce the image size and post it on the list. The last slide in this presentation, I've got a list of stuff that I'm not going to talk about, right? So if you're interested in any of those topics, right, I don't mind doing a few slides on that and maybe presenting in a future 4th 2020 meeting. So I'm going to talk a bit about steering, speed control, acceleration control, feed forward, and also there's a slide towards the end, and hopefully I'll get to it, to do with fourth controller maths. So this is sort of interesting. This is the intersection of trying to do a bunch of stuff which maybe you want to do with floating point doubles, but usually you can't afford that on a microcontroller that's on a robot. So there's a slide on that stuff as well, and I'd like to expand on that topic maybe in a future call. Let me just talk a bit about mouse geometry. So you think of this is mostly pertains to maze solving robots, right? So that so people have tried almost every geometry you can possibly think is a random set of 8. So the wheelchair type design that you saw right at the beginning is the top left, and that's the one we'll probably concentrate on. But people have done 4 and 6 wheel mice, and it's sort of interesting characteristics to do with the skidding of wheels as you turn. The top right is trying to illustrate using a steering wheel, although people have tried to do it as a wheel that gets dragged behind the mouse as well. Bottom left is a balancing robot. Those exist as well. So there's a huge number of them, and ones that turn the wheels as well exist. But most of the mice are the 2-wheel sort of wheelchair design. So this is a picture of one of my other mice. It was actually built, the hardware was built by a guy called Ken Hewitt, but I write the software for it. And this is sort of what you're looking at from a basic mouse. So if you're in, and some of the mice still stop in the middle of every cell and decide what to do and then make a 90-degree on the spot turn. But nearly all of the mice nowadays are constantly running, right? They don't stop. So obviously, as soon as you spot that's a green, the big green arrow where the wall ends. As soon as you spot that, you've got to be planning for a turn. Part of this depends on whether you're running in explore mode or fast run mode. And I won't go into the specifics of that, but obviously once you know where the maze is, you can make some educated guesses as your mouse is running around. But when you're in explore mode, you obviously need to spot that wall coming to an end and decide to make a turn if you're doing a running turn as opposed to an on-the-spot turn. And you don't really want to stop, right? Stopping on every cell is an expensive thing, especially as these things are timed, these competitions are timed. So these, just skipping on to the acceleration profile before we have a conversation about controllers. This is sort of a typical acceleration profile, if you like. So to start, I guess, from the end and work backwards, obviously you don't want to apply full motor voltage to your motor terminals. That would probably be a bad idea. Skidding and sliding is very, very difficult to control for. So you want to be in control of the mouse all the time. So you want to slowly accelerate up to your straight speed. If you remember the picture, the small picture of the maze. So if we go into the second cell, not the first cell ahead of us, and get to that sort of straight speed as fast as possible without losing grip. If you're going to turn because there's a wall ahead of you in the third cell along, then you need to, usually your turning speed isn't the same as your straight speed. I guess intuitively most of us know that. So you need to decelerate to your turn speed. So you need to predict when you're going to get to the turn. Obviously, part of this depends on your forward sensors and when you're going to detect that there's a wall ending and where in the cell you start the turn for a smooth turn. So all those sort of parameters you have to work on. And then you perform your turn at another speed, and maybe you're going to stop there because it's the goal cell, right? So you have to decelerate down to hit a particular target. So obviously things like static friction for starting off and kinetic friction and inertia and momentum all come into the setting the speeds and the acceleration. Obviously there is a heavier mouse gives you downforce, but the negatives regarding the energy to accelerate and decelerate and the increased inertia or angular inertia are generally much worse than so you're trying to make your mouse as light as possible, which obviously gives you less downforce on your mouse, which limits your practical acceleration rates. There has been lots of conversations about whether this sort of linear acceleration up to speed is the right way of going about it. Some of the people have suggested that we should perhaps be controlling torque. Now, torque is on a DC motor, if you're not using a stepper motor, torque is proportional to the current, if you remember that. Field theory lectures maybe at university, not voltage. So in theory, you could put maybe if you knew the performance of your tires and the surface, you could set the current, the maximum current you run through. But generally, voltage is easier to control. So people taking voltage control using some sort of PWM on the motors, and then that effectively limits that ends up that you want a limited acceleration. And a constant maximum acceleration is probably the easiest way to control. High-speed mice have a problem with the surface of mice. Some of these surfaces are painted with blackboard paint, which is dusty. Maybe the walls are made for MDF, and you get particulates from the walls on the maze. If you watch any of the especially the Japanese competitions, they'll go round the roboticists themselves will go around and clean the surface of the mouse, and they're always cleaning their tires. If you watch the Veritasium video, so Veritasium's a science-based channel on YouTube. There was a Veritasium video recently that starred Dave Otten from MIT and Pete Harrison, who's the UK competition winner. And one of the things they point out is whenever you go to a robot competition, you see people cleaning the wheels to get the dust off them, because it's that critical. There are obviously other approaches for being able to increase acceleration. The world-class robots, Pete Harrison's one that he won in the 1st of July just a week ago, that uses downforce fan. And all of the fastest mice in the world use downforce fans to allow them to corner much faster. To give you an indication of what that makes to the speeds, the fast mice at the UK competition were averaging about 20 seconds to get to the center. Pete Harrison's mice did it in 6 seconds, and it's cornering about 6G. That downforce is about 200 grams. So you're getting 200 grams of downforce without any extra weight on your inertia. Okay. Let me go for another 5 minutes. I'll open for questions. I've covered all of this, I think. This was just notes. One of the sort of simple things you can do that is advised by several other robot people is don't use raw PWM. So when you start this, usually people go, right, okay, I'm going to PWM. I'm going to use that as the output of my controller. The problem is batteries obviously aren't constant voltage, right? So if you PWM, you're effectively varying the voltage in the motor terminals. If you're talking about lipos, which are very, very popular on robots, that I mean, maybe anywhere from 4.2 to possibly as low as 2.7 volts. That's a massive scale. The same applies for nickel metal hydride batteries. They're not constant voltage. So what you probably want to do is scale your is actually generate your output to your controller system should generate a target voltage, and then your PWM is based on the current battery voltage reading against the target voltage. It's a simple thing, and when somebody's pointed out to you, like, well, that's obviously logical, but it's one of these sort of things that can affect your control performance greatly. And obviously, you need to set a maximum target voltage to allow for your battery dipping over the run. Okay, let me just talk a bit about steering. So, effectively, your mice it'd be great. One of the tests is to do open loop control down a long straight and see how long it can maintain the close to the center of the maze corridor. It's good to be able to have open loop control that's pretty good, but you're always going to have, especially with turns and slip on acceleration, you're always going to have some offset between the wheels, so you end up needing to correct that. So the diagram on the top right sort of gives you an impression. The red arrow, the inside arrow, is close to where the inside edge of the mouse is relative to the wall. The green arrow, the extended arrow, is where it should be. The grey arrow at the top is the current mouse vector. Obviously, what you need to do is correct that. The easiest thing to do is to create some sort of angular rotation, or rather a reversed angular error, and then add it into your rotation control. So I'll talk about that a bit in a minute. I'll put some stuff in light grey. Generally, the steering and the speed control and the position control are all going to be independent PID controllers. In reality, nearly all the mice drop the I term, right? Because they're constantly moving. If you take position, for instance, then it's really pointless to try to get to a steady state because the mouse is always moving. So the I term's pretty much useless for Micromouse. The D term, you probably want a bit of D term to avoid overshoot and decrease settling time, but not much. Most of it's done via a proportional term in your steering. I'll talk. Well, I don't know whether I'll get to it today because I haven't got a lot of time, but maybe next time I'll talk to you a bit about how you set PID parameters, because the KP and KD parameters on all systems are tricky. I remember even back as there are some excuse me, rules of thumb, and also some advice on the internet, which is probably it's very domain specific how you set controls up, but there is some recent advice about setting controllers up in a mathematical way by doing some basic measurement. Let me just go on to this. I think I'm pretty much running out of time, Peter, I think. So a lot of people, well, some people control the two wheels independently. Now, ultimately, you've got to derive a separate drive voltage to each motor, right? That's ultimately what you've got to do because they're independent motors. But from a system point of view, a lot of people have pointed out that it actually makes more sense to think about the linear motion, that how fast and how far you're going as a composite for the robot, and then treat the rotational components separately, whether that's position or rotational speed, usually referred to as omega. So treat effectively turns and linear motion as two separate entities and have two separate sets of controllers for them. And then at the end, right at the end, just before you set the motor voltage, effectively you the angular rotation is a difference, you end up with a position or a speed component and a angular component, and then you have to subtract one away from another to get the angular and add them together to get a what's called. I'll cover that maybe in a different slide. I did start on a slide to do with how you combine all of these components, but I didn't finish it. I think probably there's a few more slides. I don't know how much extra time we've got, Peter, because shall we stop there and resume the rest of it at next time? Are you there, Peter? He's frozen in time.
Well, perhaps if no one has any real objections, you could continue for a few minutes.
Yeah, sure.
Yes, let's go on a little bit.
Okay, no problem at all. So this is what I was referring to about PID tuning. So experimentally, so there's a couple of pieces of advice. I mean, for some systems, some domains, tuning a PID controller is well understood. But for a lot of robot problems, that they've got unique challenges, and the Micromouse is no difference. And if you're trying to do experimentally, you know, maybe you set the proportional component, and the equation at the top right is your, if we ignore integration, is your sort of your PID controller equation. So setting KP, the constant, as maybe a tenth, you might start with that and plot the performance. So the graph in with the black background, the bottom shows an acceleration and then a constant speed and deceleration in terms of speed. You might set that as a tenth, and then you might set KD as a hundredth perhaps, and see what it is, and then you play around with KD. Now you've got, I guess you've got two options with this. You either create a test kit that is equivalent to the inertia of the robot, and obviously remember that your turning performance or turning characteristics, turning KD and KP might be different from your linear KD and KP. And the problem is that this trial and error can actually give you and this graph on the right actually shows this. It can give you a performance. This blue line matches the characteristics we're looking for very well, but the orange line is actually the output of the controller, which is terrible. Your motors are not going to survive very much when you're almost putting maximum, minimum, very high frequency energy into the motor and try to control it. So although it appears to be a good speed control, in reality, it's actually a bad controller. So there's another way of doing it, which is to effectively measure or try to measure your controller characteristics. So a couple of things you can measure. One is this graph in the middle with the different color lines is to measure your final speed for a particular input voltage, effectively open loop it, and then also estimate your 63% point, which gives you your sort of time constant for the system. Then, because the motors themselves are a first order system, but the mouse plus the feedback system is a second order. And obviously, as a lot of you know, second order systems are very well understood for control theory. You might want to have a damping ratio. So if anybody remembers control theory, damping ratio 1 is the critically damped. You might want it a bit more. You might want it a bit faster than critically damped. So I think it's half of root 2 or something is 0.707. Gets you within 5% the most quickly. You also need to figure out your natural frequency, which is probably related to your time constant. And then there is a couple of equations that you can put that into to effectively give you a KP and KD that's reasonable for usual Micromouse. If you're interested in this, I'd advise you to look at this presentation, this YouTube presentation that Pete Harrison is a UK competition winner did. It goes through this in great detail and goes through these graphs. These graphs are actually Peter's. This gives you an idea. So obviously, because you've got several of these controllers, it's sort of critical that you get them right. And one of the big things is controller tuning. There are other controller system types that maybe are a bit easier, but generally people end up on a PID controller. The other thing that you might not consider is adding feed forward. So for some systems, it's impossible to do feed forward because you've got a varying load, and maybe there's other variables that it's very difficult to approximate. But we can measure the mass of the robot. We know what the motor and the drive chain is. We know what the load is. We know what the crested and current speeds are. So we can actually create a feed forward system. Now, what's the advantage of having a feed forward system? Obviously, you need a feedback system. You can't just use a feed forward system. You're not possible to eliminate all errors from the system. You know, I mentioned dust, for instance, on the board is one of them. But what it gives you, perhaps, is even if you've got a relatively poor PID controller, all of the controller's trying to do is correct the offset the feed forward isn't producing. So once you've tuned your feedback controller, then you can add in a feed forward controller to give you a much better overall control. And that's relatively simple to do. The last slide is this. I'd like to do, this is sort of something I'm very interested in, and I've discussed it with maybe at least with one other member of the 4th 2020 group. This is to do with how we do the maths for the controllers. And what I'd like to do perhaps at a later date is to have is to actually go through some Forth code about how you do this. A lot of people effectively go for fixed point maths, and it's certainly possible. I'd probably like to give some examples where it's tricky, or where you need to do the scales of the things, like some of the constants versus some of the figures you get out of different bits of the system, mean that 32-bit fixed point is mostly okay, but occasionally you have to do some range management, right? Surprisingly, floating point maths is actually applicable, even if you're doing a 2 millisecond control. On the robot we run on Arduino Nano, which is an 18 mega 328, not fast by today's standards, 60 megahertz processor, and you can do it's receiving encoder pulses at the kilohertz range. It hasn't got a quadrature encoder, so it's manually doing the quadrature decode for the two encoders on the wheel shafts, and it's also doing the ADC readings for all of the sensors on board. But you can still effectively got enough processing power to do the various PID controllers in floating point in software. However, generally a lot of the Forths don't have the floating point maths libraries, the open source ones. So you're probably building your own support. Obviously, if you've got a micro, maybe like the Cortex M4 on the STM F411 with floating point units, then obviously that's blazingly fast. Things like the Pico, the RP2040 haven't got a problem either. They're just the ESP32 would be another one. They're so fast that floating point maths don't bother it, even if you're doing it in software. Theoretically, you can do it in integer maths, although it makes my head hurt when I'm doing very small KD values and stuff. You end up doing effectively manual fixed point maths, which is probably much harder. So I've covered a whole bunch of stuff. I've got a list. As I said, I'll try to put this slide deck up. I've got a list of other things as well. So if there's any topics on this you want me to do a deep dive on, or any of the other topics involved in mice, I know somebody put something up on maze solving today. So lots of people involved in maze solving. Any of these sort of topics, then I'm happy to do another presentation.
I think just quickly,
Cool.
Don and Atle have had their hands up for a while.
Sure.
No, I'm just wondering, are you doing some kind of of a Monte Carlo random sampling and to predict where you should be and then read where you actually are and then minimize the error. Are you doing stuff like that on this Micromouse?
I don't think so, if you understood your question. So it depends on which system you're talking about. I mean, the infrared sensors have got a problem that it depends, obviously, the distance to the wall. If you're talking about steering, the distance to wall depends on the reflectivity of the walls, and you will see people calibrating it based on the competition walls. But it's quite a noisy signal. Effectively, you end up with this sort of exponential curve on the reflected light, and you need to translate that back to a distance. Also, these mice, obviously, if you're just about one meter a second, right? You've got that's in 2 milliseconds. You've traveled 2 millimeters. You know, so they move very quickly through the cells, right? So although you can afford some level of filtering on some of the input signals, you can't afford a lot of it, right? And the faster your mouse runs, then the more problems you've got. In terms of distance sensing, they use a odometry to do dead reckoning. So for the encoders, the encoder pulses, we maybe sample 2 and then do an average of 2 or 3 to find the approximate speed. But we also count those readings and do dead reckoning. Now the problem is, over the time running through a maze, they do lose, because, you know, you get wheel slip on acceleration, deceleration, no matter how good you are. So what people do is they look for the edges of walls and try to resynchronize the cell position on those edges. Additionally, if you've got a very long straight, so it's not unusual, especially for the American competition, for them to have a straight round the edge, to have straight runs of 16 cells with no exits. So that means that you potentially have got to be accurate to a good to a quarter of a cell over 16 cells, which is very hard. The one possibility, if you're struggling with that, is the posts between the walls actually always give you a constant blip on your IR sensors. So some mice actually use that as to reset their position in the cells. It's a topic in itself, I guess.
Cool. I have Don Golding.
Yeah.
Okay, great presentation. I'd love to hear more details on it. First question is, the first part of the competition is you're allowed to explore the maze so you can determine your path. Is that true?
Yeah. Yeah.
Okay.
I mean, so I mean, in the last couple of years, the rules have been sort of more standardized. It used to be in the Japanese and Korean competitions, because of the number of entrances they had at one point, they limited the total amount of run time, and then it was the fastest run. So, and sometimes they limited the number of runs as well. So you might have 5 minutes to run, and you got up to a maximum of 5 runs or 10 runs, and they didn't really care about the explore time, apart from the fact it was taking off your total time. So the UK competitions, the UK rules used to be that your score was maybe let me get this right, was a 19th, so a 19th of the explore time, that's to the center cell from the start to the first time you found the center cell, plus the fastest run. So that'd be your score. A few years ago we simplified that. In the early days, obviously explore time was a large amount of time. Most mice explore much slower, safer speed. Not all of them, but nearly all mice explore at a slower speed, and therefore all the competitions, the explore time, apart from the fact you might only have a 10 minutes to a maximum to run the maze, the explore time doesn't count. So you can afford to perhaps think about different strategies to see whether you've got the shortest path. And it's tricky to design an algorithm if you don't know the entire maze. It's tricky if you design an algorithm that works on every single maze. There is a GitHub page that one of the guys who maintains with all the competition mazes that have been run since the mid-80s across the world. What you find for the maze solving algorithms is it's tricky to come up with an algorithm that gives you the optimal route for any single maze. But you can do things, for instance, a lot of the mice run, that they assume there isn't any walls. So when they run back to the start cell from the goal cell, once they found the goal cell, they'll tend to take cells that haven't been visited before, because that might be a shorter route. The other thing that some of the competition winners do is they look for the cell that's next to a cell, and they'll make that a temporary target to try to explore more of the maze. So if there's cells on the way back that they haven't explored, they might go and explore those to see if there's a shorter route. So there's a bunch of different strategies people are using to try to find the shortest route. Some of the Japanese competition, I think, has got a rule about going into the start cell again. So because they're limited on the number of, not only the time, but the number of runs you can do, they won't go back to the start cell. They'll go back to a cell that's just ahead of the start cell, so they don't trigger the next run, especially when they're still on the explore maze. I don't know if that's answered your question. It's a topic in itself. I could talk for about an hour on it.
Please do.
Rob, this is
one last
amazing.
question. Any FPGAs being used?
It's an interesting question. I don't know for definite. There's a guy that's doing a camera mouse. He's got he works at Canon or something. I'm not sure whether he's using a SoC or an FPGA on that. It is an interesting question. I mean, it's certainly possible to do it, right? The power budget's not really a problem for mice, even on small lipos. Sorry, Peter.
Rob, this was an amazing presentation. You are always invited. We want to learn more about this fantastic theme and topics you presented on the group. And please do next month another one.
Thank you very much, Peter. You're very kind.
Oh, fantastic. Then, Cornelius, which is the next participant?
The next one up is Matteo Vitturi with arcade game sounds on AY chip using .afx file format. Matteo, take it away, please.
Okay. I think that I'm here. Can you see me? I put the real hardware here in front of my desk because the sound doesn't go through the Zoom system. So I hope that I could play something just to introduce the topic. Let me start. Okay, I think that's enough. Did you hear something?
No, it was quiet. Sorry.
Oh, okay. I'm sorry, but I put a video on YouTube so you can hear something video. Okay, let me share the screen so I can explain what I did. This one. Yeah. Okay, I think that, okay. I move, okay. What I did, well, I discovered that the new ZX Spectrum Next has 3 AY chip, sound chip, AY389,012. And having 3 of these allow us to have a total of 9 channels, because each AY chip has 3 sound channels. So what I did is to look in the internet and see what is exactly this AFX format. I discovered that I could implement in the Intel Z80 a good routine that exploits the interrupts. So what I did is the demonstration is just this one. First, I had to take all these AFX file and put them inside the block system. So let me show a little. Okay, for example, 4490 list. I'm sorry, is divided by 2. 2200 list. Okay, you see that the screen is full of garbage because this is exactly the binary representation of such a file. Okay, then I developed a small demo that uses the interrupt. Okay, this is another thing I did. I implemented an interrupt service routine within Forth. Okay, what this means that I can create a new definition. In this case, is the AFX frame that performs the communication with the AY chip 50 times a second. So you can read a block, a standard block in a buffer, and send each byte at the right time to the AY chip. So this is very easy, but okay. Essentially I exploited two features on the new spectrum. The AY chip that okay, and the interrupt routines. That's all. When if I want to play a sound, in this case I have to explicit the block's number, which channel I want to play, and then give a play block. Sorry. Play block. Okay. Is on, for example. Okay. You cannot hear anything, but I should hear that my little emulator plays a weird sound typical of video games. I think that's all. I didn't do very much other things, but I'm very proud to show that in Forth you can implement definition and call it during an interrupt, so you can at the right time drive the AY chip. That's all. Any question? I promised it was 5 minutes. Come on.
So go ahead.
I should have put my hand up, sorry. So Matteo, was that playing from a binary file? Is that what you said at the beginning?
Yes.
Okay.
I did a great work, a great job. It was to find so many files, AFX format, and put them in blocks from 4,000 to 4,600. Okay, 4,400 to 4,600. I mean, so I use 100 blocks to hold these files, because I deemed faster than the block system is faster than open and close a file. So, well, the fastest was to have it in RAM, in memory, but it's not so affordable. So I use a block system that actually reads always the same file that is always open, is a file number always open.
Yeah.
And it put it in the buffer, so the buffer is in the main memory, so I can address this chunk of memory during the anti-interrupt. The problem is this, that during an interrupt on Forth, you cannot do everything. You must be very careful to not impair the whole system doing something that was in the main program. Okay, but
Yeah, so
yes,
so that
please.
you actually read in the block
Yes,
with the binary data in the interrupt service
yes,
routine in Forth.
exactly. I constantly read blocks that are put in buffers, and then the interrupt routine deals with each buffer. So my experiment was that I was playing up to 7 buffer contemporarily in the same time, at the same time. It's far enough. It's a mess, I mean, of sounds.
So this is a Z80 where you're emulating it, but it's a Z80 at 3.5 megahertz.
Yes. In this case, the next goes to 28 megahertz.
Yeah.
It's 8 times faster. But the interrupt service routine goes 50 times a second as usual. It's just it's simply faster. It's quite a bit faster. 28 megahertz is quite better.
Yeah.
3.5 is totally not enough.
Very cool.
That's all.
Excellent. Nice stuff. Are there any other questions? Not the case? Good. In that case, next up is Bill Ragsdale. He prepared a video presentation which I shall share now about structures of vocabularies on WinForth 32. Let's do the screen sharing. Movies and TV, share sound is on, and here we go. Play button to me, play button.
Well, good morning, good afternoon, good evening, wherever you are in the time zones around the world. I'm Bill Ragsdale, the founding president of the Forth Interest Group. And many, many years ago, it was so long ago that we did our programming on clay tablets. But enough about that. Let's talk about vocabularies today. We'll cover vocabularies mostly from the perspective of Win32 Forth, but it should apply to all the Forth that you have available. So when the vocabularies have been used over the history of Forth from the very, very start, and the utility has expanded, the methods have expanded with over time. Today we'll discuss the addition of also to the original vocabulary structures, some of the support words that aid in the use of vocabularies, and I'll offer a couple of cautions on the use areas where we might get into a little bit of trouble. So why do we have vocabularies? Well, in modern day Forth, there are so many words available through a variety of applications. We need to segment them for usability, for quick search, and for ease of memory. In most Forths today, you're going to find at least 3 vocabularies: the core vocabulary Forth itself, an editor, and an assembler. And there may be some equivalents to those in the systems you use. Instead of an editor, you may have a integrated development environment. For example, Win32 Forth has 14 vocabularies. We'll discuss them in a few moments. So these segment the groups of words by their usage. Similar words, similar applications, similar purpose are in a given vocabulary. An element that is a great benefit is that by segmenting into vocabularies, the compiler's search is simplified. Instead of searching every word in the entire system, you can selectively figure which vocabularies will be searched. Also, vocabularies aid us in recalling words. If we're working in the assembler, we only have to remember the assembler words and their use, and don't clutter our thought process with words from other vocabularies. In this way, they hide unnecessary detail, which is a component of contemporary programming. So what is vocabulary? Well, The Forth dictionary is composed of words, and a vocabulary is a linked list of the words that are in the dictionary, and they're identified by their particular name. Word searches are done by utilizing a vocabulary name which specifies the vocabulary and the order in which they're to be searched. The key word here is search order, and we'll certainly talk a lot about that. The syntax associated with vocabularies specifies the vocabulary in which new words are added, and it also specifies the words in which words will be searched. A bit of history. Back in the 1960s until about 1982, the vocabulary structure was tree structure, as we see here. The blue line in the center is the Forth vocabulary, and branching off from it, we see the assembler, the editor, and the application. A key component of this is that the linkages were fixed when the vocabulary is defined. So the vocabulary here of assembler was designed very early in the system, and so it links very, very low toward the base. Editor was defined later on, it links a little higher, and then an application highest of all. And then the Forth vocabulary was continued to have additions made to it past the application point. This is the way vocabularies were searched back in that time period. The key words are context and current. The context vocabulary is used for searches. The current vocabulary is used for additions. So when we specified the context vocabulary, in this case, it's application, a search would start at the top end of application, continue down toward the arrow, it would join to Forth, and it would search the remaining Forth down to its base. If the word was not found in the context search, the search process went to the current vocabulary, which is illustrated there in green. The current vocabulary is the vocabulary into which new words are being added. So there were two processes of search first context, then search current, and that's it. The vocabularies were linked at the time of creation and could not be altered. You could not change that particular linkage. And also in those days, forgetting could have some serious side effects, because if you were to forget too deep into Forth, for example, you could leave another vocabulary hanging with no termination, and the system would hang up. Also, we found that in those days, more than about 5 vocabularies added difficulty. You had trouble remembering the search order and which vocabulary linked to which one. You had a little bit of trouble on forgetting and so on. So it was common in those days to reboot the complete system if you wanted to create new linkages. You would do some editing and then you reboot the system. And in 1982, I proposed only an also at the 1982 formal conference. At this case, the vocabulary search order or the linkage is not determined at compile time, but it's determined by the syntax of words using vocabulary. That search order can be determined at any time by using specific words to alter and create the search order. So at this time, from this time on, vocabularies became independent. The Forth vocabulary has a beginning and an end, same with the editor, assembler, and applications, and they do not directly interact with one another. Incidentally, in Win32 Forth, the vocabularies are divided into threads. This is a hash method, so that within each vocabulary is a series of sublists divided by or accessed by a calculation process called hashing. The purpose of having these threads is to speed up searching. Instead of searching an entire vocabulary, if you had 100 threads, you would search 100 times faster than if you search the entire vocabulary. And the cost of having a thread is just one memory cell or 4 bytes. So expanding when you have megabytes of memory available, a few hundred bytes to speed up the search is trivial in cost. In Win32 Forth, the default is 19 threads. So to create a vocabulary with that default, you simply execute the word vocabulary, followed by the name of the word that you wish to call that vocabulary, in this case, a vocab. If, on the other hand, you wanted to specify the number of threads, you can do that with a word named number sign vocabulary. Here we see 3 number sign vocabulary will declare a B vocabulary with only 3 threads. The thread quantity should be odd and preferably prime, as you would expect from a hashing calculation. Here we see the vocabularies within Win32 Forth. Incidentally, it has 14 of them. We've simplified here on just showing the most used vocabularies. At the top is Forth. We see it has 331 threads and it contains 2,447 words. This means there are only 7 threads of words per thread. So imagine if you were searching for a word like dupe, which is the bottom of the vocabulary, you would have to search through 2,400 and roughly 47 words to find it. By hashing, you only search 7 words and you're guaranteed to find it. Some of the vocabularies are there, but they really are not utilized. The vocabulary called hash has a bunch of system words in it. It has 629 words and through 79 threads, but it's very unlikely you would use this in application. And so that's one of the advantages, one of the reasons that vocabularies are used, is to get those words out of sight. The assembler has 43 threads, 16 words per thread because the assembler is used less often, similar for disassembler. The files, every file that is opened in Win32 Forth has a corresponding word in the files vocabulary. And when a system boots up, it has referenced 84 files, and therefore there are 84 file names in the files vocabulary, but there's only 1 thread because the time of opening and closing a file is significantly longer than the search time, and there's never a large number of threads in that vocabulary. So it makes do quite well with only 1 thread. The locals vocabulary right now has 1 thread and no entries because these were the thread entries are the locals entries are only made when local variables are declared. And finally, we see the root vocabulary. It is the most basic of all. It only has 3 words, and we'll discuss that in just a moment. So what does the search order look like? Well, in this case, it has been created by executing the sequence only, Forth, also editor, also application. The search order is just as you would expect. It's created a new list and it accesses Forth, editor, and application. These are stacked up in the green section at the left, reading from the bottom to the top. The most accessible in the search order is application, then editor, then Forth, and then finally root. And these are stored into an array called context. It is actually a physical location in memory as an array named context. When a search occurs, it begins at the top of the search order, which is application. That will then search the yellow list at the bottom. If the word is not found there, it goes to editor, searches the green list, goes to Forth, searches the blue list. And if it is not found there, it tries the root vocabulary. And otherwise, of course, as we know, it tries for a number. So how is this put together? Well, the context is called a sticky array. It's similar in some ways to a stack in that it grows, additions are made at one end, and it gets larger and smaller. However, it differs from a stack in a very important way, and that is that the top entry in the stack, using a vocabulary, places its entry as over the top of the word in the stack. So that is, unless no other action is taken, each vocabulary name just replaces the prior vocabulary in the search order. To begin, only clears the array and places root at the bottom. Then, as you execute a vocabulary name, it puts its name as the most recent context entry over the top of the one that's there. So how do you make room for a new vocabulary? You execute the word also. Also duplicates the most recent context entry, and it makes room for an addition. So when we say only Forth, if another vocabulary would be named, it would overwrite Forth. So we have to say also, and then the new vocabulary, such as an application. previous drops the most recent entry. And finally, the word definitions sets off to the side a little pointer to the vocabulary into which new words are placed. Most of the work is all done in the context array. And then when a new word is generated, the context pointer, the current pointer specifies that vocabulary. We'll talk a little bit about the root vocabulary. It's only 3 words in Win32.4. It's the word set order and fourth word list and the word fourth. We'll only look at the use of the word fourth for the time being. So when you execute only, root becomes the basis of the search order, and the only useful word you have available is to then say fourth. So if you execute only by itself, you can only find those 3 words, and of course you'll then utilize fourth. So when interpreting, only is almost always followed by fourth. There's no other use. There's a limited use for those 2 other words. So a typical declaration would be only fourth, also application definitions. In this case, application and fourth. And the application is the vocabulary into which new definitions are going to be placed. One of the very interesting, valuable parts of this structure is that the search order can be compiled. So in this case, I've declared a word setup, and on execution, it will set the search order to be only for also application definitions. So anytime we want to go back to that original setup, just execute the word setup, and you'll reliably return to that particular search order. Another use that's a little more obscure is that you can actually seal an application. For example, if we have an application whose words are given on a menu list, if we execute the word setup, which we'll call only menu, only clears the search order, menu is placed into the search order, and at that point the system will only find the words in menu. That's not quite true, but for the moment we'll say that only that words in that menu will be found. It's best to include an escape word somewhere in your menu so that you can get back to your application. Otherwise, you have to reboot the system. Well, actually, we know that within the root, which is always present, fourth is present. So you can always escape by using the word fourth. Here's a note of caution that's developed over the years, and that is that the word previous can be hazardous to your programming health. Imagine that you use the word previous in a file that's called by another file. When you get back to the calling file, it may be very hard to determine the search order. And so you have to look back in the code and figure which file has called which file in what order to determine what the search order actually is. When I created only also, I intentionally did not include the word previous, because it was my intent that if you made elaborate changes to the search order, you would declare a new one rather than adjust the old one. Also, forgetting can produce uncertain results in the search order. Win32.4 does use a smart forget, so that when you forget words in Win32.4, it unlinks them word by word across all vocabularies. And so as far as I'm able to determine, the forget in Win32.4 is bulletproof, but it can be a problem in some systems. So the solution in this case to uncertainty or the use of previous is the rule is that a file should exit with the same search order as existed upon entry. This is like being a good neighbor. You go to the beach and you enjoy a beer. You don't throw the beer can away. You pack the beer can out. So a file should leave no litter on the programming beach. A file should exit with the same search order with which it entered. If you do use the word previous, it should be within a file and also only within a page or two. So if you add a vocabulary temporarily and then a page or two later, you back up to eliminate it with previous, no problem, as long as it's easy to the programmer to search a couple pages forward or back to see what the change was. And as I pointed out before, the safest way is to compile the search order in a colon definition. That way, when you want to know the search order, you execute that word and your search order will be correctly established at that time. This whole process is very structured. It facilitates the clarity and the reuse. So here's an example of compiling search orders. This is a real life example taken from Win32 Forth. The word in Forth sets up only Forth definitions, and this is the core to the system, the basis of the system. When meta compiling is going on, it sets up a search order that is only Forth and adds a VI image, which is virtual image, and it adds meta, and then it makes the definitions of the words go into the meta vocabulary. When a new system comes into operation, you then execute in transition. At this time, you will only get the words forward, target, and transition. Notice that the old words in the old Forth and meta have all disappeared, and you're only using these vocabularies which apply to the new system. So we see here how this vocabulary structure allows you to create programming environments that are significantly different during the phases of your programming. So here's a couple of keywords that are very clever, and that is, it is possible to preserve the search order and restore it. So if you wanted to alter the search order, and yet you want to go back to what it was, executing the word get order copies the whole search order to the data stack. If you had, say, 7 vocabularies in use, the pointers to all 7 goes on to the data stack. You can then change the search order, do some further work, and then set order will restore the search order back to the stack. So if you're coming into a file and you were unsure of what the search order was, you can say to put get order at the beginning of the file, do your work, and then say set order at the end, and you'll return without having changed the search order. So to summarize our little adventure here, only also caught on immediately. All the systems, or most of the systems, after its introduction, began to use it quite enthusiastically. I'll also comment that this was presented at a very memorable 1982 formal conference. Formal conferences were held by the Forth Interest Group, had a worldwide attendance. They were in Monterey, California, and we'd have about 100 attendees, 150 attendees over a 3-day conference. At that same conference, Chuck revealed his new create does form. Up till that time, we used what's called build does. That was somewhat irregular in internal structure, and was a tad different than all the other word structures in Forth. When Chuck came out with the create does, the inconsistency was removed, and again, immediately everybody switched to that new particular form. So what we're seeing now is that only and also are beneficial for applications, for clarity, for convenience, for memory aids, and so that concludes my remark. I'm delightful to be here today, and I will now return the floor to our noble leader.
Cool. Thank you so much. That was impressive. Do I have questions?
I'll yield our question time because we're way behind schedule. So please continue with the meeting.
Excellent. Cool. Thank you so much. Next one up is Brad Nelson with ESP32 Forth Corner, dividing ESP32 Forth. Brad, take it away. Brad, we can't hear you.
All right. Can you hear me?
Absolutely. Sounds good.
All right. Okay. And I assume you can see the slides. Great.
Yes, we can.
All right. So the focus of this talk is the fact that ESP32 Forth has gotten too big. It's gotten there as one does, slowly, bit by bit. What happened? Well, a bunch of stuff happened. Way back, it was, oh, here's this OLED module. We should add that in. And then I got an ESP32 cam, and so, got to add some camera bindings. And at some point, I added floating point, and then serial and serial 2 support, and Bluetooth serial. And there were a couple of functions that required C-style structures, so there's a structures vocabulary. There's files, there's SPIF, there's blocks, there's timers, there's sockets, there's Wi-Fi, there's fault handling, there's a visual editor, there's interrupts, there's SD cards of various sorts, there's IDC, there's heat management, there's LEDC, a bunch of different stuff. And it's even worse if you look at sort of the non-ESP32 pieces. There's a bunch of bindings for Win32. There's X11 stuff. There's a bunch of graphics operations, and even a software implementation of Bezier curves and threads. So way out of hand. And there are a bunch of different reasons it's gotten here. Some is just that different applications want different things. They, especially for ESP32, we make use of a lot of different C code. It's easier for me to ship one big release than to have lots of separate variants or different flavors of a thing. And really the real reason is just that it's easier to add than to remove or refactor. And so I got to do something. How big is too big for a Forth? I think this is something I've long struggled with. I think that there's a broad spectrum of possibilities. I think Dr. Ting felt that even dual loops were probably a bridge too far, but there was enough demand for them that I added them. But about value 2 or locals or structures or tasks or graphics, where that line is about how much is too much, I think depends a little bit on what you need as a user of a Forth, and also sort of the complexity that you're willing to tolerate from the tools that you use. ESP32 makes this particularly strange because its resources are a little bit weird. There are multiple types of resources, and they have different levels of scarcity and different things that you could add to a Forth use them differently. So RAM is weirdly more scarce than flash. There's 4 megabytes of flash, but something on the order of 400 to 500 megs of RAM, depending on how you want to count it. And so this means that words that are defined in Forth are more expensive because they have to go into RAM, whereas things that I'm able to stuff into the flash are sort of cheaper. But it also means that things that are changeable are harder to, are more expensive. And then because so much of what we pull in is really bindings for C libraries, some of those C libraries have themselves rather large dependencies, as though things like the Bluetooth library ends up actually gobbling up a huge amount of space. You can easily fill up, on the order of like several hundreds of kilobytes with the Bluetooth library. And then the other wrinkle is that different models of ESP32 have different amounts of RAM, but also almost more significantly different amounts of contiguous RAM for various reasons. Some of the models are able to give you a big contiguous chunk, and others have stuff in the way. And so you can, for allocating something like the Forth heap, that's easier to think about. If it's contiguous, this becomes a bit of a problem. But of course you have to be careful too, because some libraries rely on there being non-Forth memory still available in the system. So lots of tug and pull, which makes it a problem to just have the thing grow without bound. So what could we use as a limit? Like different Forths over time have used different limits, and I struggle with this. I sort of envy in some ways the creators of the Jupiter Ace, for example, were able to just say, okay, we're going to use an 8 kilobyte ROM. I'm going to stuff as much as I can into that 8 kilobytes, and that set the limits, and they stuffed a surprising amount in. G-Forth, I'm not sure I can say if there's a particular bar they use, but it looks like they kind of hew to what's in the standard library, maybe with a little bit of exposing the stuffing of sort of the details of the implementation that bleed out. And then Win32 seems to just sort of throw in anything because it's, you know, it's running on a desktop system, and sort of there's just a ton of stuff in there. So I thought to myself, well, what has actually helped me kind of keep things from getting even more out of hand? And I think one early thing that I ran into was, you know, I had folks that were expanding the system, and I got the idea of adding a user extension hook, user words, and I think that that's helped some. I used to sort of feel like, oh, if Peter or someone asks for a thing to be added, if it was, you know, if it made sense for and others might benefit, it's really easy to imagine adding it. I think it's also helped actually that people complained about it getting too big. It's actually given me a little bit of incentive to feel like, okay, yeah, if it's so big that folks are having trouble building it on particular boards or building it when they add in their own stuff, making some noise about it gives me an incentive to feel like I'm accomplishing something by shrinking it. It doesn't always feel like removing things is making things better, but when you realize that there are folks that are, you know, out of RAM or out of flash with the device, that's helpful. On at least for Linux and Windows versions of the thing, it's been helpful for me, I think, to at least not have everything get built into the core executable, and so having some stuff out in external files. I mentioned Bayesian curves in software, and at least that happens to sit out in an example down in an example directory in the so I think that if you have them, files can end up at least for things that can be implemented in Forth being pretty handy. I mentioned the user words hook. For those of you who haven't seen it in a while or used it, there's this option to, if you place a user words file, userwords.h, next to your ESP32 Forth.ino, it will pull in this file and it will look for a macro called user words that lets you add in additional word definitions using this peculiar macro syntax. And that lets you extend the system in a way that you can update the version of ESP32 Forth you're using and just place your header file alongside it. And you're free to include addition, if you want to be more modular, you could include additional header files from there. There is a hook, it's been a while since I added this, but I don't know if I've ever talked about it externally. There is actually a user vocabularies hook in there as well that you can use if you happen to want to add your own, add your word in a way that makes it easier to move it into a vocabulary. There is a syntax for that as well. It's a little bit tricky because for those of you who've looked at the internals of ESP32 Forth, it's not that the system is able to boot up and do vocabularies immediately. Vocabularies are implemented actually in high-level Forth to some extent. So when you specify a vocabulary for a word, what you're actually doing is attaching it to this magic built-in. And so this will create a word called myvocab-built-ins. And if you transfer that word between vocabularies, all of the built-in words attached to that will move with it. And so this is not so much a way to define a vocabulary, but a way to package a bunch of built-in words so that you can move them easily in one swoop, while keeping them in Flash. Importantly, the reason for any of this stuff, things would be a lot easier if it could all just be in RAM. Unfortunately, one possible way to avoid some of this peril is to use files more with ESP32 Forth. But of course, the problem is a lot of the extensions that are the most interesting are things that involve C libraries, and those unfortunately rely on the Arduino tools and rely on a rebuild, and so that doesn't work well. The other problem is that even for things that you can define completely in Forth, getting things on and off of the device isn't always easy. You know, sometimes you have your ESP32 connected to the network, but not always. It would be, you know, you could imagine having some kind of a download site and then maybe a package manager or something really elaborate to do that. And there isn't really good tools I've found for doing some of the back and forth file transfer. The most convenient thing I've actually found is with devices like the ESP32 CAM that have an SD card built in. I'm too lazy to wire one up to another board, but having an ejectable SD card, I have, at least for some of the development I've done on ESP32CAM, found that I can put my Forth code in a file on an SD card, move it over to a PC, edit it, and then bring it over to the device when I wanted to deploy it. And that works okay when you can do it. The trouble is that it doesn't apply readily to all the boards. So ultimately, to address some of this concern, I've gone ahead and made a stab in the dark. I finally decided to break apart ESP32 Forth INO. It's a generated file, by the way, for those of you who are unaware. I actually have a bunch of make files that kind of assemble it already from pieces. So from my point of view, it's long been something that has subcomponents to it. But since I distributed it in a zip file already, it seemed like it wasn't a huge step to carve off some of the less used pieces and put them in an optional directory. And so if you download the latest beta of ESP32 Forth, you'll find that there's more than one file inside now, and it uses that same has include mechanism that I used for user words. And if for certain optional components, if you put them next to ESP32 Forth, then they'll get loaded. And then my goal is to iterate with the user community to figure out which modules should be optional. And maybe some should be optionally removable, so that maybe they start out next to ESP32 Forth by default, but are something the user can move away. So the way this works, just to talk a little bit about the mechanics, it's probably something I've been pondering whether I could even simplify this further, but this was sort of the most direct transfer I could make and safely test. There's a hook like this per optional module that you'll see in the source code, where it looks to see, is there this particular file name next to it, and it includes it, and otherwise it does not, and leaves some empty stubs. And then, for example, with the OLED module, it defines its vocabulary separately, and then is able to attach a bunch of words. There's this very first word, OLED source, which actually, rather than living in the OLED module, lives in the OLED vocabulary, lives in the internals vocabulary, and it puts on the stack the address and length of a block of source code to be executed at start for this module. And so then what that allows me to do is have a fourth level hook that checks to see if that module is actually present, and then in addition to loading the C-defined words, also define some Forth-defined words, because, for example, the source code for the OLED module has both words defined in C, but also a bunch of constants defined in Forth. And so this piece of Forth code gets loaded in addition to the bindings, and so that way the amount of memory footprint that you get from checking for these hooks is basically none in the case where you don't use the module. So, for example, this gets boiled away to nothing in the C code if you don't have the module present, and then this is present in the Forth code, but this is all interpreter time code, and so there isn't anything that actually gets baked into the dictionary if you don't use a particular module. So I made a fairly arbitrary stab in the dark in terms of what I've moved off into an optional module. One that got flagged to be my Peter is the assemblers. The assemblers are not as useful as an assembler would be in a normal Forth, and not everyone needs them, and certainly not everyone needs them taking up flash footprint. So I've moved them off into their own module. There's also, with the assemblers, they were actually being a little bit wasteful in the sense that if you loaded them on a RISC v5 device, you would get the Extenza assembler and vice versa. And that's been fixed up so that now you only get the assembler for your platform. There's a bunch of plumbing for the camera that was only relevant to ESP32 CAM. I picked that one to move off partially because it's specific hardware, not everyone has it. And also, although there was some attempt in the macro logic in the system to pull in this code only if you had something that was likely an ESP32 cam. The reality is that there isn't a good set of macros that are defined for the ESP32 cam for some reason. It doesn't have a good way that you can from source code determine if it's present. So this will make it more explicit. The other confusing thing is you can actually use the camera module from the ESP32 cam as a separate peripheral. There's this OLED module, and I pulled it out just on the grounds that I figured it was one particular OLED module. It's not even the only one out there. So I figured the handful of folks that care about that module could move that file in. And then serial Bluetooth is another one. This one's mainly just because it's really big. And so making it something that you could just explicitly put in seemed like that was a good choice because it's a large one. And then the SPI flash stuff, I added it mostly because I wanted to poke around with the partition table on the SPI flash to see if there were things that could be done with managing it in different ways. And so it wasn't clear to me this was of general use to everyone else. So this is the structure, and the way it works is that if you download this and just go ahead and load this INO file, everything will install just the base set of stuff. And then if you wanted to use one of these optional modules, all you need to do is move them up a layer so that they sit next to ESP32 Forth. Potentially, there are a bunch of candidates, maybe the LADC support. There's a bunch of stuff for FreeRTOS tasks, a bunch of stuff around GPIO interrupt triggers that is pretty low level and specific. I'm not sure if anyone's using it. Timers, you can do most of what you would do with timers probably better with tasks. There's stuff for the remote control. There's support for remote controls in ESP32, and I don't know if anyone's using that. Maybe the web server, the sockets, or the files. Certainly, maybe the visual editor. I imagine not all of you are using the visual editor on device. IDC support, maybe floating point. Floating point, way back originally, I made it. There's enough of a seam. I probably could make it something you could toggle on and off. It might be hard to do it as a module, but maybe not. It's possible it can be done cleanly. So love to hear feedback on this from the group. Are any of these a mistake? Some of these maybe I picked the wrong pieces to pull out, or maybe I should make some of them on by default. What else should I leave out? Is there a good general principle that I could use to decide what's in or out, and how to grow this thing in a healthy way? And with that, are there questions?
Great talk, Brad. Excellent. We wait for that. Atle and Don. Atle, I'll go ahead.
No, I was just thinking about those first Linux kernels that you got with the Yggdrasil Linux, where you compile the kernel and you would only enable the stuff that you actually had. There were no modules. Everything was compiled into the kernel. And so if you didn't enable any of that, you got something that might be able to read the disk and might be able to write to the screen and not do much else. And I like that. I like to be able to have a kernel that only consisted of the drivers that I needed. I remember compiling drivers for SEO, Scenics, and I like the simplicity of it. So I love this approach that you're doing, and as you can take it, as far as I'm concerned, you can take it as far as you want to.
Glad to hear it. Yeah, as folks try it out and bump into versions, let me know if you hit any rough spots or confusion with it. But my hope was this was simple enough. I considered things like putting a configuration option in a file, and I figured just moving around files would be the most sort of obvious direct thing. And let's see if we'll see if that works. And if not, we can always change it. So.
Don?
I vote for the web socket support, and specifically building an interface to Bard.
Yep. No, that's definitely one that would now make sense to put in a module. We wouldn't want to build that into every piece of it. But.
Excellent work. Excellent.
Yeah, that addresses one concern that I had with ESP32 when I started looking into it recently. What is all this stuff, and do I really need it? Because it's a lot. Good. Any more questions? Because if not, we have a coffee break ahead of us. How many minutes do we think?
10 minutes is okay for you all?
Perfect. In that case,
That's
10
fine.
minutes. In that case, 10 minutes it is. I'm going to pause the recording. So for a few minutes, you will be completely unsupervised.
USB blaster, but
I
on
wanna
the
see
inside,
this.
they are very, very different. So the one that everybody seems to have, I have a few of these, and some of them work and some of them don't. Inside is an STM32F100 with I think a buffer chip. The second chip on the right you see is a buffer chip, and it has this board has a cunning little piece of foam inside it to keep it from rattling about. And then the nicer one has, if you go from left to right, is an FTDI FT245. And then after that, you've got a Max 5 CPLD, and then you've got the same 245 buffer. And the nice one, obviously, even on the inside, it just feels nice. Everything looks like a lot greater quality. Having said that, the ones of these that work, they work. Not much else to say about it.
Mine doesn't.
So this is truly a case of you get what you pay for.
Yes.
Oh boy.
The difference between those loaders comes into play when you're using very large FPGAs.
Yes.
The bit blaster type will take a long time, whereas in these smaller devices, it's really not an issue.
So what's the reference, the official reference for the quality stuff?
So
Jason?
we go on with the presentations. Now it's the turn of the workshop of Klaus Schleissiek. And
yes, I'm here.
if you agree, Klaus, then take over.
Okay, let me share the screen. I hope you now see my screen and you will see much too small characters, I believe. I
can read everything.
Okay, I'll make it a little bigger.
You are sharing your desktop, you can share the screen only. Or
yeah, but I will be going back and forth through things, so that seems to be appropriate, the way I'm doing it right now. Now, this is kind of, first I start with sort of a theoretical, oh, by the way, do you still see my board and over on your views?
yes, Klaus, but can you make your window, can you maximize the window on the left?
Which window should I maximize?
Your editor, are you talking from your
Ach so, yeah, no, I'm already changing to something else.
Okay.
So first of all, I can of course maximize this.
Yes.
First of all, I want to show you what you can get on GitHub. So for one thing, if you want to work with the board, you need definitely GeForce 0.6.2 because I had to massage the outer interpreter considerably to do elegant cross-compilation. And so I had to do some patching of GeForce, and until GeForce 1.0 will be available, that is the state of affairs. And once we have a stable 1.0, I'm going to port the system to this contemporary GeForce version. And so I here have a repository with GeForce for Windows 7. It doesn't work anymore on Windows 10, sorry, but this is how it is. So it has an exe file, a PDF, which is an explanation of GeForce itself, and this how to install is very important too. You have to follow the steps. And today we are talking about two things. There is a repository Microcore, which is at present not in the latest version because the latest version is on the board and I have to port it back. Microcore is kind of the abstract Microcore without being attached or specialized for any board. So if you do your own design for some other FPGA technology or some other board, you would, the best thing for you to do is to start with what you find here on Microcore. Let's briefly run through the directories, documents, all kinds of stuff, important. Getting started, microcore.pdf. So this talks about the VHDL code. And then we have Microforce, and that talks about the software aspects of it. And everybody who hasn't read Microcore overview, you should do this. This is, I think, a 6-page document or so, and it gives you the broad ideas of Microcore. And the public license is there as well. Well, in a nutshell, you can do everything with Microcore you want, just like the LGPL or the BSD license, with one exception. You are never allowed to claim that when you use Microcore in any application or in anything that is derived from it, you are not allowed to claim that this is exactly according to the original model, because this is a marketing idea I learned from 2 English lawyers. Under the assumption that Microcore becomes a success and industry is going to use it, industry wants a standardized version, and I or my hairs want to earn money in doing the standardization work and the work that is needed to certify the adherence to the standard. So, but I mean, this, if you just want to do your project, that is no limitation whatsoever for your work. So these are the documents. Then there is the model sim directory. These are files for the wave window to give you the signals you want to do, and these are specialized to certain things. And the microcore.mpf is the file that can start model sim with the proper files then integrated. Another one is software. Well, of course, that contains all the software there is, and this is it. No need to go into that now. Simplify, I have been using Simplify standalone when I developed Microcore, so this is just like Model Sim. It has a project file, and what is FDC? I think FDC is simple, yeah, simple settings. And then VHDL, of course, is the VHDL code itself. So this is let's call it the abstract model of Microcore. And Microcore has been used to operate it on a simple lattice prototyping board, which I'm using for the last couple of years. And then Peter talked me into porting it to the EP4 CE6 board, which I have done. And as I hoped for, just an hour ago, I was able to find the last bug in the SDRAM code. And now you have, and I have prepared, this is important. If we go to VHDL, we see an architectures directory, and in the architecture directory you have a 16-bit cell address, a 16-bit byte address, and 27-bit cell address, a 32-bit cell address, and a 32-bit byte address version. All of those integrate the SDRAM, and it gives you, well, lots of RAM. And then in these directories, you always find 3 files, which are the architecture description for synthesis and the architecture description for simulation. There's little differences because, for instance, there is one constant, logic constants called simulation, which I use, and sometimes in the code I decrease the number of ticks of some counter or whatever, which would otherwise just waste time in simulation. And then the micro data cache, that is the internal, that defines how the internal RAM is being produced for the different word widths. And for instance, with Altera with the EP4C6, that is not capable of automatically inferring a RAM structure for the 27-bit version, and then in the 27-bit version I'm including an IP generated. I can just show this to you to make the thing clear. Oops, architecture, let's go into the 27. Is this readable for you? Well, the specifics are not important. Here you see I have defined a component generated by the IP generator, and then attached I have this entity that has been generated, and so it will actually use this generated file when you do work. And you see here what is unusual. The size of the memory is not a power of 2. The size of the memory is just 6K. And whenever you use something that is not a power of 2, then my abstract model, my inferable model of a RAM, it fails. And so you have to put an IP generator, generated RAM into the design. But I mean, I think using this oops, where are we? Using this file mu data cache VHD, I contained all the dependency as far as the internal block RAMs is concerned in this one VHDL file. And so here you find a set of architecture descriptions and data cache descriptions for all the different versions I prepared. Beside that, here then in the architecture directory, I have also included the configuration files that you need to work with the board. So if you use any of these sizes of the board, you don't have to start the Quartus design environment. You can directly load these into the board, and then you can just concentrate on using the software, and we come to that later. Okay, so much about the VHDL code. What else do we have? Oh, that's it. I mean, this is what you find at GitHub. And I can only say happy hacking at that point. So I leave that. Okay. What else do I want to talk about? So if you do not have a, let's get back. If you do not have a Win7 system, but a Linux or iOS system, then you have to use a Docker file, and I have described this in the chat where you find it. It's, oops, I don't remember off the top of my head. Also in the LFX protoboard, you find a file which I have not yet prepared for the new board, for the Altera board, which is getting started.pdf. When you start to work with it, you might want to take a look at it. I mean, in principle, the steps are exactly the same, but this talks about the LFX board, and in the next week, I will prepare the same kind of thing for the new Altera board. Okay. Oops. Perhaps I now go through this whole rigmarole of things, what to do. And so we have to start with loading the proper version into the FPGA. I have done this already with the 32-bit byte address version. And can you at all read this tiny little characters here? Well, so what I had done is, or if I change the architecture that I want to be using, I take these three files, I copy them, and I drop them into the VHDL code itself. Einfügen. And so I say yes, yes, yes. So now we have updated the files. And then you go to the software directory and start a command shell in it. So this is where we now are. And then I call GForce. And well, this is the GForce salutation screen. And then I can say, for instance, inside software, you see that I have quite a number of load underline files. I can, for instance, just say, and here you see the file which is called load.fs. I have prepared this, but I will start with something else. So I say include load underline core.fs. So this is the file that has a test of every instruction and which can do a memory test. So, and I load that. And it tells me, for instance, in core test, m divide mod is not yet tested, but what the heck. So, and here it says it has produced 3,305 instructions for the whole test suite. And now I can run this on the board. I just say run. And then it does a handshake with the board with through what you can see is important is this line here, which is a prolific, or actually it's a logic link, but I recommend prolific because prolific, to my knowledge, is the only serial adapter which does not wait. If you type on the keyboard, then usually the adapters wait for, let's say, 100 milliseconds or so, if there is coming another character. And the only designer found that immediately ships even single characters is prolific, and that has a dramatic effect on the speed with which you can work with the board. So this here is the umbilical link, and which connects to the host computer, of which you see the screen. And the handshake means that both the cross-compiler debugger on the host synchronizes with the design in microcore. And so there is a little bit of code that is used for the synchronization and for the control. And so if it says handshake, then everything is fine. And the microcore prompt shows you that now we are inside the board. And so we can do a core test, and it comes back with a 0. I can show you if I make a mistake somewhere. So if the hardware doesn't work as it should, I can model this. Oh, u divided by 2. That is a bad idea. Let's make a memory mismatch or something in the arithmetic. Yeah, I say -2 instead of -1 at this point. And then I have to go out of the board again. I'm back in the host. I can again say include load core.fs run. And now I do the core test. And it didn't make any difference. Now this is very strange. No, yeah, this was with the saturation arithmetic, and I used numbers that saturate. So here we can introduce an error. And you see now core test doesn't display a 0, it displays a 20. And then I search through the file core test.fs and I see 20. Okay, it was in this line. And here we have the problem. I put the 3 back, and then everybody should be happy. This, by the way, is the load screen for the load core. So the load screen loads the core test, and then I also prepared a memory test. So we will load the proper version again. Now we get no error, and then we can do the memory test. That takes a while because this is a 32. So if you don't believe this, this is really a 32-bit version. And we can also do byte addressing. Like if I did the memory test, and the memory start X10 starts at hex 4000. So if I do 20 dump, I see this is what I wrote into the memory, and this is what I checked again. The dump function, this is one of the debugging functions which are available. And I also can do 4000, let's say 20 C dump, in which case I will get the bytes one by one after the other. And what do we see? Something strange. I wanted to make a least significant first system, but it turned out that I made a little endian system, but as you can see from the dump, I did a big endian system, which is not exactly what I intended. Let's see whether everything is fine here. 5000, 4000 store, ST. Talking about ST. ST is the basis for the store, and since, I mean, in one cycle, you cannot drop 2 items off the stack. I mean, you can at most drop 1 item. And so ST stores the number and does a pop, but it retains the address. So if we do this 5000, 4000 ST, then the address is still there, and we can do a fetch and a dot and see, okay, at least the system is consistent in itself in that everything is big endian right now. I'm going to change that again.
No, it is not.
It is
not. No, look, at where you set the 20 dump, your 4000 colon, in that field you have 400, next one 4004. If you look at C dump, the very first byte is the 0 of 4000. Then you have
that is this 0 here.
Yeah, that's
this is not even little endian, right? This
this is, look at the 4004, the next cell. So the 5th byte in the dump from the left. So you have 04000. That's your first field. Then the next one starts out
I get your
4.
point. So I introduced a high quality bug somewhere. Let's see what.
Yeah, but for 32 bits, this is little endian what you have there.
But if it is little endian, I should go from here in that. Are you sure?
And you are. Yeah, you are.
So let's see what happens if I do a 4000 word fetch.
You should get 0. No, sorry. If you do a 4000 word fetch, you get 004.
I get the 4000.
Yeah.
And if I do 4002 word
fetch, you get 0.
I should get 0.
You said you would do a 4004.
Wait a second. What
is dot?
Yeah. I stored 5000 there on this line. So there is no longer 4000. There is 5000.
Yeah.
And if I do 4002, word fetch.
You get
dot,
null.
I get 0.
Yeah.
So everything is fine.
Yes, bona fide little engine. You're good. No bug.
Okay. Still, I am a little bit, this is numbers, yeah. A little bit puzzled. So, okay. So you see byte and word and cell addressing works nicely now. It took me a while, and the difficult part was to fiddle with the addressing scheme, and because I address bytes, the memory is 16 bits, and on a 32-bit system, I'm talking about 32 bits. And so on a 32-bit system, I always do, if I talk about the SD-RAM, I also always fetch 2 items out of the RAM, and I get 32. And then computing this into bytes and words, it took me a while to get it working. But now it's done. Okay. So where was I? This was a memory chest. Yeah, some. Okay, I think this is fine. Now I'm. Oh, this is a mistake. It says back in the host, and this prompt remained. This is not supposed to happen. So what I'm now doing is I prepared a little load file with a silly application that calls store and then store calls C, and then C does something to the LEDs. This is something I'm very proud. I'm going to show you. Load.fs run. There's also something I want to talk about. You see here, I said library forslib.fs. And the library function is something where I show you the library. So this is the library. It uses the tilde in front of the words and then another tilde, and here it has a tilde in front of moves is also one word. Sometimes I include more than one word in one tilde. The tilde is a directive to the library compiler where it makes sections of code that get the name round and get compiled on the host system, but not a single instruction gets compiled in the target. And when later on the target, when I use a word that has been compiled by the library, then the word in the host is called, and calling and executing this word results in compiling the code into the target that is associated with this word. So this way you have all the words of the library available for use, but they don't take any space, and you only have to and only those words get actually compiled which you use. And that even works interactively, by the way. So what word? And by way of saying we're both on, I get these messages of what I load from the library. And if I comment this out and I say by include load.fs run, then I no longer get all these messages, which are not very useful. So at this point, I can, for instance, use any word which I did not use yet. So like, for instance, we can say 4,000 Oh, fill and erase do exist. 4,000, 4,001, 10 move. And you see somewhere the word move uses u less, and that gets compiled on the fly and even interactively. And now we see what the result of this was. I do a C dump. You see all of a sudden, and if I do a dump, then the difference becomes even clearer. Yeah, you see. So that works interactively and with bytes. And if you have a byte system, then move and fill and erase. You see this in the library. Here we are. So I have different versions. With bytes, then the fill uses the byte operators. And if you don't have a byte system, but if you work with full cells, then you use the cell operators. So it does different things if you do, depending on the system you are using. So back to the load. Oh yeah, we want to get to the example, and the example is silly, and so I have to give silly a number, and that tells us how often it goes through the loop. And so let's do an 8, and then you should see the LEDs, and here the LEDs run with a delay of 300 milliseconds, and we can change this to, but this is not so important. The reason why I made this example, I want to show you how you work with the system interactively. So I can say 8 trace silly, and bang, now we are stopping at the very first instruction. Wait a second. Before I do that, I show you, I can look at the compiled code. So I can say, show silly. And so we see 0 question do to R2R. This is a ramification of question do exactly compiles this code. It does a call to question do, which massages the parameters such that the branch on Tor works, and so that will result in a one instruction branch. Then I fetch the I, which is either a call or it can be compiled as an instruction. A good point to get into that. I have several compiler switches or constants which are defined as booleans, which work as switches. So one is simulation. If you see, this is the version that does the synthesis, and then simulation is at false. And if you get the constants for simulation, then it is set to true. So that is a big difference. Cold boot. Well, it has to do, if you press, it depends on, when you press the reset button, you can do 2 things. You either then force the system to jump to the reset vector, or you can force the system to execute the cold boot routine, which routinely gets executed when you fire up the board. So when you power the board for the first, when you have loaded the application, then it first goes through a cold boot routine, which, by the way, is this program here, and it just does a running light on these 4 LEDs in this haze. And this code gets compiled if I say include bootload.fs, then I create a boot file at the end and I store it as bootload.vhd, which is in the, you see it here, bootload.vhd, and this is the VHDL code for a ROM, basically. I want to get rid of this. So I create a bootload file, and when I synthesize the design later on, then the bootload code will be permanently integrated into the hardware. So when the processor starts for the first time, then you wind up in the bootload section, and then I can, for instance, load code that is contained in a serial E2PROM. I would have done it on this board, but the serial E2PROM on the board is so small, you cannot store meaningful programs there, so I didn't do it. If you have a bigger serial E2PROM, it's fine. The code is for the serial E2PROM is, I put it down somewhere, I don't remember. But if you, the code for the serial E2PROM does exist as an interface code in VHDL, and get in touch with me if you need it. So this is a bootload. So I was talking about this compiler switch, the cold boot. If it is set to false, then if you press the reset button, you will just get back to the reset vector in the software that you have loaded. If you set it to true, then you will jump back into the bootloader. At this point in time, I mean, just setting this to true and demonstrating it to you would require to go through the Quartus design, and which means on the 32-bit design, this is roughly 4 minutes, and I'm not going to do this right now. Perhaps we can do this in the workshop section to just show you how the complete development cycle goes. So this is code. Then we have a with multiplier. Remember, I started to develop microcore at a time when it was not, when only few FPGAs contained a hardware multiplier in the design. And if that is the case, you set it to true. If you set it to false, then the system will generate a multiply single step instruction, and you have to just repeat it for every step to do the multiply. But if you have a hardware multiplier, that is a basic, yeah, that is a one instruction, a one cycle instruction. And if you have a hardware multiplier, then for instance, you also can do a step log 2 instruction that will give you a absolutely precise logarithm by the basis of 2. Okay, then with float means, do you want to load all the floating point instructions? If you set this to true, later on in the workshop, we can do this as well, and you can see how Forth uses floating point. Just a remark about floating point. For a long time, I have been a hardcore integer number programmer until I was confronted with a situation that I had to compute the temperature from an NTC resistor reading. And this involves the exponential function. And you do not want to do this with integers and scaling. You really want to do this with floating point. And this is when I then wrote the floating point package. and it became very dense. It only compiles to roughly 500 instructions to give you the full floating point capability. And one of the reasons why, oh, well, we come to this in the workshop. And then we also have a switch which means with up download, if you set this to true, you can directly ship a memory content from a file into the data memory at a given location, or you can read the data memory and produce a file on the host computer. Just for the heck of it, I have set this to false. We can also set this to true later on. So these are more traditional, let's call it traditional compiler switches. And lately I also introduced this, oops, no, not this. This is in the architecture file. This is kind of a map of the instructions which do exist. And so you see there are quite a number of empty spaces for your instructions that you want to stick in yourself. And here you see more compiler switches, like with index, and that is the I. And just for the heck of it, now I will set this to true, and then later in the workshop we will see that the I is no longer a call, but all of a sudden it is a single instruction. And so these are all the instructions which are regarded as not so important. And in the opcode section and in the force lib, for all of these instructions, I mean, some are just macros and others are colon definitions in the library. No matter what you do here, you will have all the words available to you, but maybe in an inefficient way. And so if you, for some reason, need more efficiency at some point, then you would set these switches to true, and then they would give you also single cycle instructions. Okay, where was I? Ah, here we were. And we are now standing in the single step tracer here. We are now standing in front of the I, and that does a call. I already know that I cannot single step trace this I successfully because I'm doing return stack operations and the single stepper is not capable of doing this correctly. So I just do the call. Oops, what happened now? Ah, oops. We are not single stepping. We are just decompiling, so to speak. Oh, and here is the whole board. Here is silly. And so this is the code that gets compiled by this colon definition here. And it is, I would say it is quite close to, as we are used with force, it is quite close to the force code itself. So you see the call to store, then the, oops, this is the sequence of byte that produces the 300 milliseconds. It's 1-2C in hex. I have set the system to hex, and this is why we see hex numbers here. Then we get the milliseconds. So this is leaves a 4 on the stack, 4 times on the stack. So the milliseconds is actually a macro. And this means that you get, if you look at it, you get 4 ticks per millisecond. So you get a tick every 250 microseconds, and you multiply the 300 by these 4 ticks. And so you get the number of ticks that you have to set the system to sleep. And then we come to Tor branch, and it branches back to 1A3, and then it goes round and round and round until we are done. I now will single step this. So if we do 9 trace silly, oops, there's still the 8 lying there on the stack. I throw it away. Ah, yeah, by the way, before you go into the next step, you can massage the stack, which I have done right now. I threw away the 8 here, and now we only have the 9 on the stack. I could also say, oops, 1 plus. So we now have an A there. So you can intervene with the system. That is a very, very valuable tool. I didn't include an if else then. I should have done this in the demonstration, because then, because you can massage the flag in front of the if, you have full control over whether you want to go into the if or the else clause, and so you can single step a new word that you have defined completely, and assure yourself that it makes no stack error and whatnot. And the other nice side effect of the single step tracer is if you do a word with complex stack manipulations, that is very difficult to get correctly. I mean, one thing to help you while you're programming is Scrabble characters, and you can use the characters to attach some meaning to it and then work around on your table with the Scrabble characters. Or you can go through the single stack tracer and step your way ahead, and then usually very quickly you see whether you have done something wrong, and then you can correct it until finally everything is fine. So this reason, especially the stack fiddling and getting into every if-else clause, is why I think for me a single step tracer is absolutely indispensable. Okay. Now we are going to execute the 0, and I have done that, and now it's on the stack, and then we are in front of the question do. The question do is, let me go to the word for the do. It's in the library at the very beginning, and here you see the definition of question do. So it has the question do itself, as the cross compiler sees it, is it compiles question do, which is this code up here. So it's under minus swap 1 minus, and shoves one item on the return stack, and then it executes question 4, which in essence shoves the next item on the return stack. So then, as always with do loops, we have 2 items on a return stack. And so what you can still see this here in the decompiled version. It does a call to the question do, and then it compiles the 2R, and then the next 2R is compiled to question 4, as well as this is the tricky thing. The question query do is safeguards you from, or allows you to not going through the loop at all. So usually if in Forth, if you do a 0, do, you run through it by the power of 2 of the word width of your system. If you use a question do, you do not run through it at all. And the trick I'm using is that the first thing, the question do, the first thing I do is I branch to the end, to where the next is. And the next would check, this is a 0 and I'm done. And if not, it branches back and you start with your with the loop as you want it. So this is what the cross compiler do. It compiles a query do, a 2R and a question 4. So now we do the query do, and you see it has, we now do A9 and A, we put them on the stack, which means we will run through the loop 9 times, and we need the A in order to compute the proper I. So we shove both things on the stack, then we branch to the end of the loop. And we are not at 0 yet, so now we are back. We get to the calling the I. So we do the I call. The first item is 0, and then we call the store. I have prepared a variable. By the way, you can initialize variables. And if you say initialize, then the system collects all the initialization values you do while you are coding your application and automatically appends the initialization code to your code image as part of the booting process of your code image. So basically, although this is a cross-compiled system, you still can do the same things which you can do in an interactive force system. Okay, now we want to peek into what the heck does store do, and we can say nest. And now we go into the store code, and the first thing is we compiled item. Now, item is the variable at address C. So, and that is what the decompiler here says. And so if we execute this, oops, I was in the wrong window. Now we have a C on the stack. We store the 0 in C. And then, oops, this is tail recursion. The C, because it is followed by a semicolon, it doesn't do a call, it just does a branch. And so we now branch into C. Later on, we can do another version. Now here, the C would be compiled as a call because it is not followed by a semicolon immediately. Okay, now we go to this to the C, and here the C item fetch, and so on and so on. We see, and you see now it says it has 2 greater than signs. That means you are in the second nesting level. And if there is no colon definition that is called in C, so we cannot go into the third nesting level, but that is all feasible. Even if you have a deeply hierarchical part of code, you can go into all the words that are being called, and even the words that are called by the words that are called. Okay, so now we do an item fetch. So yes, there is a 0 we stored there. Where did we store it? Here, C item store, we stored there. We duplicate it. Now comes complicated code in order to get the LEDs going. I don't want to go into this, why this is so complicated. It has to do with the way I am controlling the LEDs. So at this point, I can say unnest, and that lit an LED. Can you see that? In you theoretically, you should see this in the picture. And we are now back at this point in front of the 300 milliseconds, which is 12C hex. I can, at this point, I could say decimal. And yeah, you see, we get the 300. Then the milliseconds compiled us the 4 times. Okay, and now we have 1200 ticks. And again, we can say nest. And we do a sleep. Ahead means this is computes how long we want to wait. And is the time elapsed? Yes, the time is elapsed by now. We go out, and now we are here at the end of the loop. Actually, this is a Tor branch, which is a single cycle instruction that looks at the number of the return stack. If it is 0, it goes to the next word. If it is not 0, it jumps back to the loop. So this is just like we are used to it in Forth. So we go back, we do an I call for, we wait, and so on and so on. And now I said to myself, I'm tired of going through the loop. I know that this works, and I can say after as a command. And that executes the loop to the end. If you could see the LEDs on the board, you would have seen them moving. Then the second item on the return stack that was shoved there by the query dupe is thrown away. And then we do an exit, and back we are in the target system waiting for the next input. So that is what you can do with a single step tracer. Now, how can you control the LEDs? That is another important and interesting thing to mention. If we go to the file constants to FS, the constants on this side, we have the names that have been defined in the VHDL code. Wait a second, I have to go even a step further. So I call what I have done a hardware software co-design environment, because what I have defined in the architecture file, namely this section on defining registers and bits within a register. So this is a status register, and that these are the VHDL node names of the single bits. We have a DSP register, a data stack pointer, a return stack pointer, an interrupt register. So here we have by the way, we have a timer interrupt going, and I have defined the timer interrupt service routine. You see here, if I have several interrupts, which in this case we only have one, I can fetch the interrupt flags, and I get all the flags that are set by the interrupt. And that, but for some reason, there may have been 2 interrupts hitting at the same time, and then I won't find 2 flags set. I can, for instance, say int flags fetch dot, and it always shows 0 because the interrupts are much too fast. And then I do a number e. Is it the number e time interrupt? And this is why they are here. They are the e time interrupt is defined here as number e dash time. I have a convention, and the convention is that whenever I'm talking about constants, then I put a hash in front of it. So I always know, this is a constant. This is different with the registers. With the registers, I just give them names. just like variables. And so there is first the interrupt section code. If I want to add an interrupt, I just would, in the VHDL code, of course, I just would add another interrupt constant here, constant E dash external, for instance. I give it a bit number. And then I have to say, okay, I have two interrupts. And that is all I have to do in order to introduce a new interrupt in the system. And of course, at some point, I have to write a piece of VHDL code that controls the IX bit in order to create the interrupt. And the I external would mean, well, there's an external pin and I shove it through two flip-flops to get rid of metastability, metastability problems. Yes, thank you. And then it would just set this bit. And that's it. And then later on, and then I would have to also make this I time, which defined in VHDL, I have to make this known in the force environment. And that is the reason for all these definitions. Like in VHDL, this is always a bit number. And in force, we need the power of 2, I mean, a number that allows you to do an AND or an OR on that. And so this is what the bit does. It does a power of 2 and creates a constant. And so we have number CLED. First of all, let me redo this for the moment. Okay. And as you can see, we have number hash, number C-LET0, that's a 1. And number C-LET1, that's a 2. And so now, and these are numbers in the control register. Now the control register is a very special beast that deals with all the bit outputs, whereas the flags deal with the interrupts or the bit inputs. Like for instance, I have put the keys on the board. I have just put them on these 4 flag values. So, but about the LED register. And so with the 2, I get LED number 1. I always start from counting from 0. And I just say control somewhere in the system. I mean, you don't, well, according to what you see here, I would have to say control rec, but I made an alias. You just have to say control. I do a control store, and then we see that we don't see anything. Now we have a second, the bit number 2 was set already. Now I want to switch off the second LED. So I already know this is a 2, and I just say 2 not control store, and it goes out. And I can say 1 not control store, and it goes off as well. And I'm very proud of this invention because if I do the one and I store a positive number into the control register, then I can select the bits that I want to set. Because, for instance, I could say, we are in decimal now, $F control store, and that lights all 4 LEDs at once. Or I can say $F not control store, and all go off. And that means that I can simplify my code in the demonstration dramatically, and get rid of all this rigmarole here, and just say $F control store, oops, not control store. And to make your life easier, so if I say hex F control store, they light, and I can also say F minus control store, and they go off again. Okay. Yeah, this is, just looking at the code that does this kind of magic. Well, no, let me explain to you. Then the code is quite clear. So if I have a positive number and I store it at control, then a positive number sets a bit. If I do a not, then I have a negative number where the bit that is going to be set back to 0 is at 0. And the VHDL code that controls where I store the number into looks at the sign bit. And now I go into the code. The whole, oops, where are we? FPGA point control. Here's the control register. Okay, so you see, this is how I handle registers. I have two functions, which are micro register write and also micro register read. So I have to give it the microcore bus as a parameter, and then I say which register I'm talking about. So this expression here is true when I do the control store operation. And then I look at the write data, which is part of the microcore bus, and I look at the sign bit. And if the sign bit is 0, then I take the current context of the control register and or the control register into it. So basically I set bits that are set to 1 because with an OR, the 0 doesn't affect the control register. If the sign bit is set, instead I go into the else clause and I just do an AND. And so with this bit mask, all the control bits which are already set to 1 remain set to 1, only the least significant bit gets set to 0. And this is how this magic works. And well, actually, and because I started with the notion, usually if you want to manipulate bits in a register, I mean, you have to read the register, then you have to do some manipulation on the bits, everything basically that is done here in the VHDL code automatically, and then you can set the register with the newly computed value that had to include all the bits in the register. With this technique, you can just massage a single bit in your register and it will do whatever you need to do, at the expense that in a 32-bit system, you can only massage 31-bit output lines, but what the heck? I mean, this is so nice because it makes the software so much easier on single-bit things. Okay. So much about the massaging the single bits. Then, oops, where are we? Then we can use at the flag register. First of all, let's say what number F-E0. And I have prepared a work flag query. Oops. And this F key is set to 0. Now hopefully this is the button number 0. I switch the button. I do the same thing. Yes, it was the right button. Now we read in. Now we find that F key 0 is set. I could also fetch all of the flags by just saying flags fetch U dot, and you see there is the bit number 2, which is, this is 1R, this flag of the DSU. It tells me that the system is connected to the umbilical link. This is important in a situation where you have an application that runs in some task. Oh yeah, the multitasking system. We will get into the multitasking system. Anyway, so in a multitasking system, you always start with the terminal task that handles the interactivity with the system and connects to the umbilical link. If you have a running application where your application runs completely in background tasks, then you may pull the plug on the system. And then the flag FDSU goes to 0. And then the multitasking system finds this out and puts the terminal task to sleep. So it doesn't cost you any time any longer in the scheduler, save from one jump to the next task that may be ready to run. And if you switch back your serial link, then FDSU goes through again, and then the terminal task is started again and linked into the scheduler. And then you have still interactive activity again, under the assumption that you know which version of your code is running on the system that you want to maintain. Because if you get it wrong, then of course the system that is running and the code for the interactive control don't match, and that won't get you anywhere. But if they match, and this is why it is so important to have a version register, for instance, in the hardware. So here on this level, I can say version rec fetch and print this as a decimal number. And we see we have version 1.2. So you are always in control, more or less. Yeah, so much about the flag register. Why do I have all these blank spaces here? Oh, yeah, here is the version register. So this is the version register, and the version register is what I do on top of the architecture file. Here you see version is, oops, at this point it is still set to 1132. Why is this? Why is the heck is this the case? I don't understand my own code now. And it has byte address with, yeah, it's a mystery. Why is this set to 1132? I don't know. It should have been set to 1/200 because obviously I have synthesized the 1.200 design. What else do we have? We have the debug register. Now the debug register is a register that takes care of the umbilical link. So you can do a debug register store, and that gets shipped into the host, and you can do a debug register fetch, and that reads back what the debug register, what the host has sent to you. As far as I remember, the debug register will wait until there is a character. So if I do now a debug register fetch, the system will hang. And if I do a debug register store of some number that is also dangerous, because then I will break the rules of the handshake between the host and the target system, and I will no longer be able to communicate to the target because the host won't know what to do with the number that I'm shipping, because this has a strong protocol. And this is how the communication is being done. And actually, I have called this monitor, and that is actually, if we talk in Forth terms, this is a quit, because this is a quit loop. What it does, it sends a 0 to the host store. So this is the debug register store. This is just a macro for debug register store, and we can see this if we say show monitor. Then we see host fetch, host store. So this is F9. This is the debug register address. And yeah, that is not so important. I want to not fiddle around here. I let it at monitor for the moment. So it sends a 0 to the host, and then it waits for the host to send it an address where microcore is supposed to call, so to execute. And this way you can interactively execute any word, like for instance, if I here say 8 this was again the wrong window, 8 silly, then the umbilical takes care of shipping the wait a second, I can in the host system I can by the way, order tells you where we are. We are in target, and root, and we compile into target. And if I say H for host order, then you see I'm searching Forth, which is the Forth system on the host. Now I can say umbilical on, and then I go back into the target. And now I don't quite understand why this happened, but what the heck. What I wanted to do is to show you what happened. whenever I do a carriage return, there is something happening between host and target. When I say call, there is still something on the stack. No, there is nothing on the, so this is what happens. So this is the communication that happens on the umbilical. So I say 8. Okay, now I ship the 8 to the target system. Somewhere here we should, here we see the 8, and then the target system sends back an acknowledge to the host, and so on and so on.